Okay, this is the February-March 2017 question 5 on reaction rate. The reaction of copper 2 carbonate with excess dilute hydrochloric acid is used to investigate the rate of reaction. The balanced equation for the reaction is copper carbonate plus 2 hydrochloric acid goes to copper chloride plus water and carbon dioxide gas. The apparatus used is illustrated below. So here we've got a conical flask, a scale, the copper carbonate lumps in here, and the dilute acid. So obviously what's going to happen here is you can see the flask is completely open, and you can see in the products aqueous, liquid, gas. This gas is going to bubble off here, and the scale will then register the decrease in mass, and the decrease in mass can only be due to this carbon dioxide gas escaping. State 2 ways in which the rate of the reaction above can be increased. There's a lot of ways. You can add a catalyst, you can add heat, increase the concentration of the acid, you can powder the copper, what do you call that? The copper carbonate. Powder the copper carbonate to increase the reaction surface. You could write that as increase the reaction surface. You can stir it. Stirring also adds mechanical energy. Things like that, any two of those will increase the rate of reaction, but the most obvious one is to powder the copper carbonate and increase the concentration of the acid or heat it. Then it says to you, during the investigation, samples of both pure and impure copper carbonate of equal mass are used. The reaction graphs below are shown below. Okay, so even if this wasn't labeled, you'd know this was the pure one because the mass is decreasing more sharply, okay, which means the rate of reaction is faster. It says to you, write down the reaction time for the reaction of pure copper carbonate with the hydrochloric acid. So if you look on this graph here, we need to use the pure graph, which is the solid line. And if you have a look here, you have to figure out where it goes flat. Okay, so we need the time scale here as well. Let's have a look here. It's not flat, it's not flat. Somewhere between 40 and 50 it goes flat. You have to pick. Okay, it's not at 41, maybe 42, maybe 43. I would guess somewhere around 44, 45 seconds. Okay, and if you check the memo, it gives you a range of marks, but basically it's wherever the graph went flat, because no more carbon dioxide is being produced, so the weight doesn't decrease anymore, so the reaction is now complete. So somewhere about 44 seconds. The memo gives you a range of answers. It says, assume that all the gas formed during the two reactions escapes from the flask and that the impurities do not react. Calculate the average rate of the reaction of the pure sample over the first 20 seconds. Okay, so we're going to make an equation here that the rate is equal to the change in concentration. Oh, it's not a concentration, because what is our graph in here? It is in mass. Change in mass over, remember I can't put a fraction, so I'm putting the divide, the change in mass over the change in time, because any change in time gives you rate, and we have to multiply this, whoops, wrong button, sorry, we have to multiply this by 100 to get to a percentage. Okay, so let's work it out. The rate is going to be the change in mass. Remember, we need 2 points in a graph anytime we find a rate. So we started out at 170, and we are going to subtract the mass at 20 seconds. So you need to be able to read this graph accurately here. This is 169,75. This is 169,8. So every two blockies is 100th. So this is going to be 169,76. Okay. And then we are going to divide this by the change in time, which we can write here, 20 minus 0. We should actually be going 0 minus 20, and we're going to get to a negative answer, but it doesn't really matter because they usually like you to have the positive answer. So then what we should be going is minus the change in mass, because we're looking at the reactants. Either way, it'll work out fine like this, because remember, reaction rate always must be positive. So if you plug those things into your calculator, you should end up with 0.012 grams per second. Okay, so that is going to be the average rate. Remember, this is a curve, and so the average rate is drawn by that straight line between the 2 points. Now it says to you calculate the percentage purity of the impure sample, and it's only 4 marks. So when I first looked at this, I thought, okay, there's this long, complicated, involved way to go about it, but because this is only 4 marks, there must be an easier way. So what it boils down to is this. In both of these two started out at 170 grams. So if they were both pure, they would both produce the same amount of carbon dioxide gas. We know the mass of carbon dioxide gas that was produced because we can check from 170 grams to whatever this reading is. That's going to be the mass of carbon dioxide produced, because it's the only thing decreasing the weight of the container. However, with the impure sample, the mass only goes to over here, okay? So all that we have to do is the difference in masses of these two is going to relate to the percentage purity, because the more pure the impure one is, the closer it will be to this final volume. So we literally only need the 2 changes in mass, okay? So the change in mass of the pure sample, okay, is going to be 170 minus whatever this final volume is here, which is 169.717273. Okay, so it's 170 minus 169.73, which is going to be 0.27 grams. Then we find the change in mass of the impure, and it also, remember, started with 170, and we're going to take away 169.75767778, 169.78, which is going to be 0.22 grams. Okay, so then this is the mass of carbon dioxide produced, okay, of the impure one, and this is the pure one. So this is the theoretical maximum, 0.27 grams, and this is how much we did produce. So now if we want to find the percentage purity, we need to spell this correctly, it's going to be the mass of the impure divided by, and it's not the impure sample, it's the mass of gas produced by the impure sample, but I'm not writing this down because it won't fit. Okay, so it's the mass of the impure over the mass of the pure times 100 to get me to a percentage. So my percentage purity is going to be 0.22 divided by 0.27 times 100, and if you put this all into your calculator, you should end up with something like 81.48%, and this is now the percentage purity, and it's all based on the fact that the pure sample produces the maximum mass of carbon dioxide over here, and the impure sample produces whatever mass it is in relation to its percentage purity. So this will be your final answer. Now it says to you the maximum volume of carbon dioxide gas produced during the reaction of the pure sample of copper carbonate if the reaction takes place at standard conditions. This is a standard chemistry calculation here. You know that 1 mole of any gas at SDP occupies, fill in the gap, 22,4 cubic decimeters. Okay, so remember we have these formulas. N equals V over Vm, so V equals NVM, and they said to you standard conditions, so Vm is going to be 22,4. So we need to use this formula. The problem being is, do we have the number of moles of carbon dioxide? No, we don't, but we do have this formula, N equals M over M. So if we want to know the number of moles of carbon dioxide we produced, we're going to say N, okay, but first we must write this carefully so that the examiner knows we know what we're talking about. So the number of moles of carbon dioxide is going to be M over M, okay? So what mass of carbon dioxide did we produce from the pure sample? Because this is the maximum volume. And it's this what we read off here, this change in mass here. Do you remember this answer here? This is the pure sample. It produced 0.27 grams. So this is going to be 0.27 grams produced. And that is going to be divided by the relative molecular mass of carbon dioxide, which is 12 plus 16 plus 16, which ends up being 44. Okay. So you end up with something like 6.136 times 10 to the power of negative 3. Okay, you just have to put the numbers in your calculator. We know how to use N equals M over M. So that is now the number of moles that we have. And then we just use the other formula, V equals N V sub M, which I can't put the sub so easily here. So what is the volume going to be? We know this N from over here. So we're going to take this N. Okay, we worked out the number of moles based on the mass of gas produced. And we're going to multiply it by the molar gas volume, which is 22,4, which you will get on your data sheet if you know where to look. And you end up with 0.137, which is equal to 0.14 cubic decimeters. No unit, no mark. Okay, so that's how you work out how much gas is produced. Then it says, sketch a volume of the gas produced versus time for the reaction of pure copper carbonate. Indicate the reaction time on the x-axis. So this reaction time, okay, basically what it is this is a decrease in mass of reactants graph. So you can see that it goes down and it curves and then it becomes flat. And initially the rate is fast and then it slows down, which you know by the gradient, and then it levels out. They're wanting you to make this graph, instead of the decrease in mass of reactants, to be the increase in the mass of the product. So you're going to flip it so that it starts at 0, but it'll be 0, 0, and then it goes up steeply, and then it starts flattening out, and it is completely flat at whatever value you put here. If you wrote whatever's the reaction time here, you said it's going to take 44 seconds to be complete. At 44 seconds on the graph that you draw, it must be flat, and it must start from 0, 0. So here's the answer from the memo here. If you have a look here, it starts at 0, 0, which is not labeled. You've got volume on the one graph because it says to show the volume of gas versus time. So volume goes here, time goes here, and then they've written here 42 to 50. It's based on whatever your answer is. If we said 44, there must be a vertical line going to 44, and you must have this curve going up and then slowly flattening, and then being completely flat after 44 seconds, a constant volume. And look here, people, if no labels on axis, take away a point. So it's a graph drawn from the origin with a decreasing gradient that levels out at whatever time you said the reaction was over, and if there's no labels on the axis, take away a mark.